In this video, we're going to take a look at the derivatives of trigonometric functions, and we're going to do it a little less traditionally than what you might see on some other videos. We're going to look at the derivatives of the sine and cosine, not by using the definition of the derivative. Again, you'll see plenty of evidence out there for that. But again, a little less traditionally. We're going to look at the derivatives by graphing f prime or graphing y prime. So remember that the derivative is really just the slope. Okay, so we're going to take a look at the slope values of this sine function. Okay, we're going to graph those slope values over here, and that's going to point us to what the derivative of our sine function is. So there are some general guidelines that I have for this. I do have a video on graphing f prime, or graphing the derivative, if you want to check that out, but I'm just going to run through it here real fast. So the first thing we're going to look for here is any place where the slope is 0. So that means a horizontal tangent line. And we see one right here, and we see another one right here. So this horizontal tangent line, which is a slope of 0, occurs at pi over 2. So I'm going to plot a 0, x-intercept at pi over 2, and then again at 3 pi over 2. Another x-intercept, another 0. The next thing we're looking for are positive and negative slopes. So notice over here, these are positive slopes. So I know my function values over here are going to be positive. So I'm going to be graphing above the x-axis. From here to here, these are all negative slope values. So I know over here, we're going to be graphing below the x-axis, and then right here, positive slopes again, so we're going to be graphing above again. And you can kind of even see the shape of that right now. Okay. The last thing we're going to do is identify whether the slope values are increasing or decreasing. And that means whether it's moving up or down here. So these slope values go from 1 to 0. That's a decrease. These slope values go from 0 to -1, and then from -1 to 0. So that's a decrease and then an increase. So we have a decrease. Here's how that looks. Decrease. We have a decrease to pi, and then an increase. So a decrease to pi, and then an increase. And then over here with these positive slope values, these numbers are increasing. So that kind of looks like this. Okay, so we have graphed the slope values for our sine function. And as you look at this, if you're familiar with the graphs of some of the basic trig functions, this graph looks like the cosine function. So the slope values of the sine function, here they are, the slope values of the sine function, can be described by the cosine function. So if we fill this in, if y equals the sine of x, then y prime, the derivative, the slope values, are described by the cosine function. So there's our first one. Next one here. Now we have the cosine function, and we're going to graph the derivatives of our cosine function over here, graph the slopes. So once again, we're looking for slopes of 0. I see a horizontal tangent line here, here, and here at 0, pi, and 2 pi. So 0, pi, and 2 pi. And you might be making a little prediction about what you're going to see here, but it's maybe a little different than what you're thinking. We'll see here. So here I see slope values that are all negative. So that's going to be graphed down here. And here are slope values that are all positive. So that's going to be graphed up here. I see the slope values decreasing and then increasing. So that looks like this. Decreasing and then increasing. And then from here, I see the slope values increasing, then decreasing. So here's how increasing to decreasing looks. So as you compare these two, it kind of looks like your sine function, but look at them closely. It's not really the sine function. It's the opposite of the sine function. So where the y values were positive here, they're negative here. And where they're negative here, they're positive here. So that's the opposite. So we're going to say the cosine, the derivative of the cosine function, the slopes, are the opposite of the sine function. So this is the way you might see it in a couple of books if it doesn't look like this. If you take the derivative of the sine function, you get the cosine function, And if you take the derivative of the cosine function, you get the opposite of the sine function. And that is visual evidence of that. All right, a couple of examples now. There are 4 other trig functions we haven't talked about. Secant, cosecant, tangent, and cotangent. I'm going to give you 2 examples, and then I'll give you the rest of the trig derivatives, and you'll be able to prove the other 2 the same way I do here. I actually recommend you try the cosecant and the tangent after we look at these 2. All right. So instead of taking the derivative of the secant function, I'm going to take the derivative of 1 over the cosine function, the reciprocal of the cosine function, because that's what the secant function is. And we know how to do this. This is a quotient, so we're going to use the quotient rule. And so that is the bottom times the derivative of the top minus the top times the derivative of the bottom. We just figured that one out. It's right here. So the derivative of the bottom is the negative sine of x all over the denominator squared. So I could write it cosine squared x. I have a reason for this. I'm going to write it like this. Okay. So as I simplify, we have 2 negatives. That's 0. We have 2 negatives here, so that's going to be the sine of x. And here I have 2 cosine functions. So I'm going to take a look at it like this. And I'm going to write this a little differently and take a look at it like this. And this is a correct derivative, or this is a correct slope for our secant function. But in the books, you're going to see it written like this. What is 1 over the cosine? Well, that's the secant. And what is the sine divided by the cosine? That's the tangent function. Okay? So if we take the derivative of the secant function, the result of that will be the secant x times tangent x. Okay? And like I said, the cosecant is very similar to this process here. Here's our first one. Next one, cotangent. So instead of taking the derivative of the cotangent, we're going to take the derivative of, let's see, since the tangent is sine over the cosine, the cotangent is going to be the cosine of x divided by the sine of x. And so for this, we're going to use our quotient rule, bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. So this time, again, just strategically, I could write out the sine of x times the sine of x, but I'm going to write out that notation for a specific reason again. All right, as I simplify, I see, let's see, sine squared x, cosine squared x here, they're both negative. I'm actually going to factor out that negative and write it this way. And this is an identity that you probably learned in pre-calculus. It's one of the Pythagorean identities. This simplifies to 1. Okay, so we have negative 1 times 1 over the sine squared x, which then we're going to simplify again. So 1 over the sine is the cosecant. This is going to be our negative cosecant squared x. So if you take the derivative of the cotangent x, you're going to get the negative cosecant squared of x. Tangent is, that proof is done similarly to this one. Okay, so that's it. I'm just going to leave you with this for your notes down below here. This is the derivative of all 6 trig functions. I would recommend that you memorize those as soon as you can.